So geometric sequences and their relationship to exponential functions. So suppose you make a long-term investment. We talked about compound interest in investing money. You invest $1,000 at a fixed interest rate of 8%. It's 8% every year, but it's compounded annually, once a year. The institution where the money is being held pays out interest during the year on a prorated basis. So prorated means it uses the correct calculation and it finds the interest for that particular part of a year or part of the compounding period. Okay, so most, well, not most, I don't know most, but some investments are like that. So if you don't take it out at the end of a cycle, then they will pay the interest. Some will, some won't. Okay? In this case, they will. So in other words, if you take money out of your account partway through the year, the bank will pay you the interest that you have earned up until that time. So looking at this as an exponential function, the relationship between the value of the investment A after t years can be shown. So take a look. Here's the equation, the exponential. So we start with 1,000. 1.08 is 100% plus the 8% per year, and t is the number of years. So we talked about that investment formula already a couple days ago. We've done a table of values for you. Notice how we start here with t equals 0. That's the initial time, right? And the value is 1,000. So on our graph here, the horizontal is the number of years, the vertical is the value, and so we have a y or z-intercept in this case. Okay? You've done all the calculations, so you do not have to enter that. You could graph it if you wanted to with the function, but we've entered those. If you were, let's say, you were to enter this into your list, okay, and do a regression, it may not work out to be exactly this value there, those values. Why do you think that? You enter these in to your list and do an exponential regression. Why do you think it might not be? Adam? Rounded, exactly. Here we've kept them to the nearest cent, but if you actually do these calculations, probably past about here, they go to more decimal places. So they'd be very, very close, but not exact. Okay. All right, so that's what it looks like. And there's some questions to answer regarding this. So let me just do a tool so we can see it. Okay, it says, what do each of the variables in the equation represent? So the variables are A and T. Remember, A, I call that the accumulated amount. It's the amount or value of the investment after T years. So A is the value of the investment after T years. And I just talked about that. Why does the table of values begin with t equals 0? At time 0, you're investing $1,000. That's the initial value. Whenever we did applications, exponential applications, we always had t equals 0 being our initial value. Okay, so okay, so why does the table of values begin with t equals 0? In order to show the initial value. Value, then so based on this information that I just said there, where the bank will prorate your interest if you take it out early, Do you think you should join the points up? Well, I would say yeah, because then that will show how much interest you'll get, right? I mean, do you have to? Not really, but this represents a continuous function. And if we're allowed to take it out early, then say we take it out after 2.5 years, we would go up to our graph. And so, right, and then across here, and we would then know the value of our investment at that particular time. So I'd actually say in this case, I would join them up. But if it was the case where you don't get a prorated interest, then I would just leave them as discrete points. Okay, so get out your calculator, Kelly.
Is that hallway?
Yeah. Same word as this. I guess it has a flashing between them. Doesn't get asked to. Okay, so use your calculator, find the value of investment at the end of 15 years. So take a look. At the end of 1 year, this is your investment. T is 1. At the end of 2 years, T is 2. So at the end of 15 years, T is 15. So 1,000, bracket 1.08, those brackets, the exponent 15. Do that. If you wanted to graph it, then you would find the point where T is, or X is 15 to graph it. But we don't need to graph it. And we round to the nearest cent. There's the dollar symbol. So take a look at that. You invested 1,000 after 15 years. Now it's $3,172.70, and you've made $2,170.17. Okay. Kind of a rule of thumb or a way of remembering. If now it's very hard to get an 8% investment. We talked about that. If what is it, 7 and 10. If you can get a 7% investment and invest it for 10 years, your money will double. Opposite of that, if you can get a 10% investment and invest it for 7 years, your money will approximately double. So it's a 7-10 habit. And you can try that out on your own time if you wanted to. Now the next one says, oh, that's not what I wanted. The next one says, use that equation to determine the number of years it would take the investment to multiply 5-fold. What do you think we mean? Multiply 5-fold. Josh? 5,000. Right. To be 5 times as much as what you started with. Okay, so we're going to algebraically determine. You can obviously do it on your calculator graphically, but we didn't specify that we likely will. on the test algebraically. So really, notice what happens when we divide by 1,000. You're going to get that 5 point. So really, you don't have to put the 5,000 in the 1,000. You can just go put 5 equals 1.08 to the exponent t. This is what increases your investment, right? So if you're told the investment is going to double, you can just go 2 equals 1.08 to the exponent t. If we have 10 times as much, you put 10 there. Okay? In any case, now, in order to solve for t, you can convert that to logarithmic form. So t would equal log is 1.08 of 5, or, who is mumbling away? Or log of 5 equals log of 1.08 to the exponent t. Okay, when you take the log of both sides, in order to get that exponent out of the variable out of the exponent. And you can tell that those are the same, right, by change of base. Question?
Is it okay that we skip the part where you write log of 5 equals log of 1.08 to the t and instead put log of 5 equals t log?
Oh, can you go right to here, you mean?
Yeah.
Yeah, okay, you can. Okay, I'm okay. Okay, and so those are the same value. If you don't have a graphing calculator with the ability to do a base, this is going to be easier. Sometimes this is easier anyway because it's that log thing, right? You don't even have to go into your mouth. So it's on a TI anyway, right? So you can go log 5 bracket divide by log 1.08. Okay, or you can go math log base, then enter 1.08, cursor to the right, 5, cursor out, enter. Okay, so it says, determine the number of years it would take for the investment to multiply 5-fold. It doesn't say what to round to, so this I would say 41 years. If we're, let's say that you couldn't take it out part way. And so we use regular rounding rules, and that will for sure get us 5-fold. Because remember, this is increasing, right? So if we extend this out to 15, and we want this to end up being 5,000, okay? It says, oh, sorry, not 15, 20.91. We want to extend this out to 20.91. Really, if I go 21, it'll be slightly higher. So for sure, slightly over 5 times as much. So that guarantees that you've made it to that 5,000. Okay? So that's another investment application. It's an exponential. And so now we're going to look at a corresponding sequence. Yes, Sunita.
So on the test, would you always like tell us what you're up to, or would you like say like if you just wrote on a question that like you can't figure out early, and like would that be enough information for now?
In something like this, we are going to tell you to round to the nearest certain, like either tenth or year or whatever. So we didn't on this one, but you don't have to worry about that. If you see though the word necessary year, okay, rounding to the nearest year or nearest necessary, that might mean that maybe, say you ended up getting 20.41. If you take it out at 20 years, you wouldn't have made it, right? Let's pretend that you get $5,000 after 20.41. If I said rounded that using normal rounding rules, you wouldn't quite have made that 5,000. So if it says nearest necessary year, you got to go against rounding rules in order to meet that criteria of at least doubling. And usually in the actual question, it will say to at least double or at least be fivefold. So that means you know that you have to make it there, or it could be more than that too. Okay, so it should be pretty clear. Usually on the diploma, they make it so that you don't even need the word necessary. Whatever you round to will be appropriate. Like whatever normal rounding rules will work on the diploma. Okay, so let's take a look at this. The value of the investment as a geometric sequence. So the relationship between the value of investment can be related to the number of terms in the geometric sequence. So here is the sequence of all of those values. Okay. So notice the first term is 1,000. Whenever we talk about sequences, we use term numbers, and we start with term number 1, because it's the first term. So this is different from year number, right? So term number 1, when we look at these investment values as a sequence, the first term is 1,000. That really relates to year 0. You might want to put that so you can compare. This relates to year 1, 2, 3, 4, 5, etc. Okay, so now when we graph this table of values, which, yes, it happens to be the values from the investment, but we're considering it to be a sequence, then when we plot these, our n value, so this is term number here, is the first one's 1. So there's my 1,000. When I graphed my exponential function, my 1,000 was on the value axis. Now it's here. These values are all the same, but they are for term number 1, 2, 3, and so on. Okay, so then I'm just going to move, just give me a sec to move slides here so that we have the other one right with it. There we go. Okay. Oh, then I have to, I need 3 slides. Anyway, let's go to the next question. We can go back and forth. So then it says, what do each of the variables in the equation, u sub n equals 1,000 times 1 plus 0 times 1.08 to the n minus 1 represent? So u sub n is the value of the term. So you can say the nth term. So why does the table of values begin with n equals 1? Because 1,000 is the first term of the sequence. So if this is just representing a sequence, happens to correspond to that investment, but if this is really just a sequence, do you join these points up? No. Okay? So sequence points we don't join in, they're discrete values. Okay? Oh. Because remember, for sequences, our n values are natural numbers, right? We're not going to term 1.3 or term 4 over 5, right? Our n's are 1, 2, 3, 4, and so on. Okay, so now now we have to think a little bit because we've done that last one. So this equation, that's the equation of the nth term of the sequence. Very similar to our value of our investment, but the exponent is different. So determine the value of the investment at the end of 15 years. So what's our n at the end of 15 years? Let's take a look back, because remember I put in the year values. So at the end of, so at the very initial investment was year 0, and that was a term number of 1. If we keep following that pattern, after 5 years, my term number was 6. After 10 years, 5, 6, 7, 8, 9. After 10 years, my term number would be 11. So after 15 years, what would my term number be? 16. So I'm going to put n equals 16 in here. So you'll notice then it gives you 1.08 to the 15, which is what you would have done in the original, or what you did do in question 4 on the left-hand side. Okay, but we were using a slightly different equation here. So what did we get that to be? 3,000. 3,172. Okay, so now using this equation, so this term value here, so basically we're saying what will n be to get the term value being 5,000. So un equals 5,000. What is n? Okay, we can go through all the same work, remembering that for 15 years, our n value was 16. So in the last, when we found for 5-fold, we found it rounded to be 21. That was the number of years. So will our n value be 20 or 22? 22. One more than the year, right? So n equals 22. One more than 22. Now, if you want to practice solving by logs, you're welcome to do that on your own time. Okay? So now let's compare them in terms of transformations. Again, transformations. Yeah, I love them. Okay? So now we graph them on the same graph. So this is term number or year number. Here's the value, okay, of the $1,000 investment. They're plotted. Take a look. They look very similar. Take a look at the distance between the diamond and the square in each. What does it look like? Does it look the same distance?
Yeah.
Yes. What distance is it?
1.
1. Okay. This pink squares is a transformation right 1 unit from the diamonds. And you can see that from the equation. So first of all, which points represent the exponential relationship? So this was, the diamonds was the exponential, and squares was the geometric sequence. What transformation would have to be applied to the points on the graph of the exponential to result in the geometric? We just said translation, right 1. Okay, so we know back from that table of values that our term number, so n is our term number, was equal to t plus 1, the number of years plus 1. So if we solve for t here, we get n minus 1. So if we solve for t and substitute t equals n minus 1 in, we get that equation. In words, the term number is 1 more than the new number, or okay, so let's do at least the first practice question together on the right-hand side. Okay, so it says, several layers of glass are stacked together. Each layer reduces the light passing through it by 5%. The percent P of light passing through n layers is represented by this equation. So they've kind of done the hard work for you, really. They've come up with that equation. Describe what each of the numbers and variables represent. So P is, it tells you, the percent of light passing through. Okay, so what does the 100 represent? The starting, so 100%, right? So that means light passes through. 100% really in this case would be when n is 0, so there's no glass. So obviously the light is passing directly through. So this is the initial percent. So the 0.95, so it says there that each layer reduces the light by 5%. So now we have 0.95, that's what's remaining. That's the percent as a decimal of light that is passing through. So we can say that, I guess, the decimal or the fraction, sometimes we just say the fraction of light passing through. N is the number of layers. Okay, write the first three terms and the common ratio of the geometric sequence corresponding to the situation beginning with no glass. Okay, so when n equals 0, we get our first term, right? So that's T1 or U1. Okay, but that's when n equals 0. So this n is the number of layers. It's not the term value, right? So sometimes variables are used in different ways, right? Then the next one would be 95. Then what's 95 times 0.95? Okay, so that's the first three terms. exponent. So in terms of this sequence, we would have our general term would be first term times 0.95 to the n minus 1. Okay, notice how, as I said, different n. This is this n here is term number. That n up there is year number. Okay, so if you wanted to use a different, you can use a k here.
Number of glass.
Or sorry, not year number of layers of glass. Sorry, getting confused with the compound interest. So that's number of layers of glass. This is term number. Okay. So here, remember. So if you wanted to, maybe you call this K instead. Right? This. If it helps you keep them different. Okay? And so why are the exponents different? Because of that fact. So the K is the term number, and it's equal to 1 more than n. So if I solve for n, I get k minus 1. That's all. So you just need in the application questions to think through what that exponent is going to be. Like, do you have to show it as a geometric? Not necessarily. Maybe you go right away to exponential form. But you need to be clear about when it's n and when it's n minus 1, etc., or n plus 1. Okay, the next one. I'm going to let you do that one. It's just another application. Okay, and then we'll just go again to do a little bit of graphing. And this graphing will graph some series, which we haven't done yet. Oh, just a sec.